know what the structure of something is going to be, what do the atoms actually have to do to the electron orbitals to make that happen? So today, bonding day 2, hybridization. And I said we could start by drawing a Lewis structure for methane. Now it's already up there, but that's okay. Let's just go through it quickly. I said the first thing I want you to do anytime you draw a Lewis structure of anything is what? Sorry? Very good. So let's count electrons for this. So carbon, how many electrons in its valence shell? 4. Good. And what about hydrogen? 1. And how many of those do we have? For a total of? Very good. So we have 8 electrons to work with. Now, which atom should go in the middle? In this case, the answer is really obvious, but carbon. And as a general rule, which one should we put in the middle? No, but just in general, when we make a Lewis structure, the atom we put in the middle should be the one that is, has the most electronegativity. In this case, that's carbon over hydrogen. So we'll put carbon in the middle. We put the hydrogens around it. And then what do we do next? We make bonds. And then we pause and stop to do what? Count electrons. And in this case, we picked a nice easy one. What do we find? 2, 4, 6, 8. We need 8. That's the structure. Nice question. You hope to get a question like that on the test. Right? Yep. Yep, of course. So there we go. That's the Lewis structure for methane. And what kind of bonds are these? The sigma bonds, right? The first bond between any two atoms is always of a type that we call a sigma bond. So altogether, carbon is making what? Has 4 sigma bonds, and it has no lone pairs of electrons. Right? Can everyone see that? This is making 4 bonds. They're all sigma bonds. They're all just single bonds. And it has no leftover electrons. And we usually call those leftover electrons lone pairs. By the way, we always deal with electrons in pairs. So if you end up with an odd number of electrons in one of these structures, either you've done something wrong or I've accidentally goofed in like the charge of the thing I gave you, but you will always have an even number of electrons. You have to, because we work with electrons in pairs, which again, we understand because we said every orbital has to have 2 electrons in it, one with positive spin, spin up, and one with down spin. All right, and then each hydrogen, what can we say about them? Very good, 1 sigma bond. And do they have any lone pairs? No, good. And they're all the same in this case, right? You could have cases where you have 2 of the same atom that have different situations, but in this case, all of the hydrogens are identical. Okay, what we want to do is talk about how carbon can do this. So let's draw an electron configuration. Let's draw an energy diagram for carbon. So carbon has how many electrons total? Total number of electrons, not just the valence. 6. Okay. So carbon has 6 electrons, and the first 2 go in the 1s orbital. I know that much. Where do we go after that? Yep. And how many do they hold? Good. And then, if we remember, if we went 1s, 2s, 3s, 2p, 3p, so on and so forth. First I do 1s, then I do 2s. What comes next? 2p. Okay, and how many real orbitals does a p have? Like how many orbitals do I have to draw? 3. And each of them can hold 2. How many electrons do I actually have to put in here? 2. Okay. Which tells me what? If I look at this arrangement, how many bonds is carbon ready to make? 2, right? Does that make sense? If we just left carbon like this, it could only really make 2 bonds. It can't make a bond with the empty orbital because remember, every bond involves sharing electrons, 1 from each atom. So this can't share. This can't share because it's already full. And so the only things that are available to share are these 2. So in this configuration, carbon only has 2 electrons to share. It's also, by the way, in kind of an awkward situation where one of those would be in the up-down, which would mean the atom it would share with would have to be above it, and the other one would be in the left-right, so it would have to be left-right. And so you would end up with this weird thing where you have like a 90-degree angle with 2 things bound to it. So not only do we not have enough room to make bonds, but they're in a weird orientation to one another. Does that make sense? Can I show that again? Like in this situation, if this is carbon, it would have this p orbital ready to make a bond. So maybe a hydrogen could go here, right? And then it would have this p orbital ready to make a bond. But then this orbital's full. So could something go here? Could something go here? Does that make sense? So we don't have enough orbitals available to make the bonds we need, because remember, it has to make how many bonds? 4. And those orbitals are in a strange orientation. They're in a shape that doesn't work well. So what do we think happens? For the record, this is a model. This is a way of explaining the behavior in the observation. I just want to be clear about that. Like, this is scientists making a mathematical model that fits the data. That doesn't mean, how do I explain this? Just understand that what we're really talking about is energy level and probability of location here. So what we want to design is new orbitals that have new shapes, so they'll hold things in different directions, and have the right number of electrons in them so that we can bound. And what we say is that what has to happen is the formation of a hybrid orbital. And so what we do is this. We start with that one at, oh, no, I don't want that to be red. I want this to be blue. We start with that 1s orbital with 2 electrons, the 2s orbital with 2 electrons, and the 2p with just 1 in the first 2. I'm just redrawing what we had before, okay? And we say all of these are going to combine to form what we call hybrid orbitals. Take a minute to write that. Now, we are making these hybrid orbitals out of what? Well, first of all, what shell are we in? Yeah, if you look, the first shell is unaffected, right? Bonding happens in the valence, so it's only the second shell that's changed. So in our new setup, if I draw an arrow here to show what we end up with, I still have a 1s, and it still has how many electrons? 2. Good. That hasn't changed. But now, in the second shell, do I have an s orbital anymore? No, because I've combined it with the p orbitals. What do we call an orbital that's a combination of an s orbital and a p orbital? Very good. We call it an sp orbital. And then specifically, we used the s orbital. How many of the p orbitals did we use? 1, 2, 3. So we call it an sp3 orbital. Kind of weird? A little weird? Yeah, you may have in biology talked about things being sp3 hybridized, sp2 hybridized, sp hybridized. I can't remember if that appears in the 12 bio or not. But anyway, now, all together, how many new orbitals should we have? Well, we combined one s and 3 p's. How many orbitals is that? 4, right? 1, 2, 3, 4. So we've taken an s and 3 p's. So one of the s's and 3 of the p's, altogether that is 4. And we've made 4 new orbitals. And they're brand new. They're called sp3 orbitals. Okay, so we'll talk briefly, but as a rule of thumb, the valence shell, unless we need to keep a p orbital for some reason, and we'll talk about when that might happen later on, the whole valence will all get hybridized to make one new orbital that can then have the most ideal shape for that compound. And tomorrow, well, probably not tomorrow, maybe tomorrow, if not tomorrow, Monday or Tuesday of next week, we will talk about the shape of these things, how this works physically given a certain shape. But basically, the whole valence shell will go from being an s orbital, which is a really awkward shape for bonding, right? Because it's just a sphere close to the atom. And then the p's, which work at 90 degrees to each other, so they don't actually work very nice for bonding either. It takes the whole valence, takes all the electrons, and makes new orbitals that are now at a good arrangement, a good shape for bonding. And again, we're going to talk about shape next lesson. Could be tomorrow. Might not be tomorrow. And the thing is, we had 4 orbitals to begin with, so we're still going to have 4 orbitals. They just have a new shape. So let's read what I wrote here. Because of carbon's electron configuration, it only has 2 electrons it can share, these 2 here. As a result, even though it needs to make 4 bonds, carbon can only make 2 bonds the way it started. So the orbitals have to change. All of the valence orbitals, in this case the 2s and the 2p orbitals, come together to make new orbitals, which we call hybrid orbitals. And we name them just by saying what we've put together. So this is called sp3 because we've put together s, and then we put 3 of the p orbitals together. So that's why it's called sp3, right? S and then 3 p's. And that altogether, 1 s and 3 p's is how many orbitals? 4. So if we put 4 orbitals in, yeah, we move them around and we change the shape, but how many orbitals are we going to get out? 4. Yep.
We only have 2 in the 2 p's.
Yep. Yeah, it includes that empty one, because now, what does Hund's rule tell us we have to do? Put 1 in each. So now, how many electrons did we have between the s's and the p's before? 4. Now, before, we had to fill that s orbital first, right? And then start filling the p. But now, these are all the same orbital. So Hund's rule tells me, how am I going to put the electrons in here? 1, 2, 3, 4. And now, what is each of those orbitals ready to do? Yeah, they're ready to receive an electron from hydrogen. So each now ready So now we have 4 orbitals, each with just 1 electron, which means we're ready to make 4 bonds. And if you look at the Lewis structure, the Lewis structure tells us we need to make how many bonds? 4. So we always want to do this and then check it against the Lewis structure. Does it make sense? When I have a hybrid orbital with just 1 electron in it, that's ready to make a sigma bond. So what would happen then is that like hydrogen would come along and put an electron there. And then another hydrogen would come along and put its electron there, and they'd be bound. You don't have to draw that, but I'm just showing it. The paired electrons would come from hydrogen. I don't know if it's helpful to draw that in or not. But these hybrid orbitals are ready to make a single bond. And so this is kind of our first rule. And I think I wrote it in text, but I'm still going to write it by hand. Any sigma bond must be in a hybrid orbital There's only one exception. And the only exception I think you know. What's the only atom that can make a sigma bond that isn't going to hybridize its s and its p orbitals? Hydrogen. Good. Only hydrogen is an exception. And hydrogen is an exception because it's in the first shell, and we know the first shell can't have p orbitals, so it can't make a hybrid with the p orbital.
Doesn't that make sense with helium too then?
Helium doesn't make any bonds at all, right? But you're right. If helium were to bond, which it wouldn't because it's already got a full shell, it would do so without making anything. Does that vaguely make sense? Is it kind of reasonable? It's a little tricky. I know it's a little weird to talk about. Good. I like this app better. Yeah, give me a sec. So any sigma bond must be in a hybrid orbital, and only H is an exception. Okay, so right away, if you've got a sigma bond, you know you're going to have to make a hybrid orbital for that to happen. So in a case like carbon, where all it's making is sigma bonds, it's in its valence, it's only going to have hybrid orbitals. Does that make sense? What else is like that? Well, in that diagram, that's the only one, right? Do you see up there? If we look at PBr3, in this case, the P is making how many sigma bonds? 3, but then it's got this lone pair of electrons. What do we do with lone pairs of electrons? Well, let's take a look, shall we? All right. So to start, I want you to draw a Lewis structure of water. And we're going to get some practice doing Lewis structures. Hopefully you all remember the chemical formula for water. I bet you don't know. Come on. Come on. Stop fooling with me. All right, so obviously those two hydrogens, they both have one electron in their valence. What about oxygen? Very good. Oxygen has 6 in its valence, so I have a total of what? 8. Good. So take a minute and draw that. It's so funny to me that we haven't done the lesson on shape yet, but everyone knows the shape of water. Just because it's always how it gets drawn, right? Like everyone is instinctively drawing it like oxygen and then angles and hydrogens, right? Did you not? Oh, probably because I didn't teach you 11 chem and constantly draw it that way. Good. I mean, that's based on what we know. That's how you should be drawing. And then based on what we're going to know in a couple days, that's how you will be drawing. So. No. No, the dipole isn't, this isn't because of the dipole. The dipole is because of this. Don't worry. Though yes, we're going to have a whole lesson on dipoles. Okay, so what should I make my central atom here? Oxygen. Good. And what goes around it? Hydrogen. Hydrogen. What do I do next? What do I do next? Cool. What do I do next? I count. Good. 2, 4. Am I done? How many do I need? 8. So I'm going to go boom, boom. Pretty sure I am. I just did it. Try and stop me.
Universe.
All right, you're right. The universe would stop me. That doesn't happen. So where do they go? On oxygen.
The universe will hate you for that.
Great. What do I do next? Count. Okay. Does hydrogen have full octet? I mean, octet. It's in the first shell. So, yep. Oxygen? Yep. Hydrogen? Cool. So there's our structure. Now let's do a little accounting. Hydrogens, which are both the same, are making 1 sigma bond. And do they have any lone pairs? No. Okay. 0 lone pairs. They're boring, so we're not going to worry about them. But let's talk about oxygen. What's it got? 2 sigma bonds. And Blaze, I heard you say it. And 2 lone pairs. Good. And so what I want to do is draw an electron configuration of oxygen to see what it looks like. I could also draw an electron configuration of hydrogen. It'd just be really boring. So we're not going to do that. But oxygen, let's take a look. Well, actually, I will let you take a look. Okay, so how does this get filled in? What's the electron configuration of oxygen normally? I should have put oxygen up here. So this is oxygen's ground state. Ground state just means how it normally is. So what do we got? The 1s will be full. 2s will be. And then how many electrons are going to go into 2p? 4, right? Oxygen has 8 electrons total, 6 electrons in its valence. So 1, 2, 3, 4, 5, 6, like that, right?
Yeah.
I'm disappointed in you, Jade Bar. You were supposed to realize that wasn't right, but okay.
I think that if I just telling you it's right, then you'll be like, maybe I should stop doing that.
Never. I appreciate that. Jade Bar, how do they go in?
So you put 1 in each first, and then you'll be like, so we need another, so then you can another.
Beautiful. Okay. Now on the face of it, this should work, right? Let's look at the valence. In the valence, we have 1 lone pair, and then we have a second lone pair. Does that fit what we said we should have?
Yeah.
Yeah, 2 lone pairs. Good. And then I have an orbital that can make a single bond and an orbital that can make a single bond, right? This should be perfect. But what shape are p orbitals? Right? So here we have like ML is 0, here we have ML is 1, right? We have those 2 p orbitals. One of them is going up and down, and one of them is going front to back, right? I'm going to spin the side so we can see it. One's going up and down, one's going left and right. That makes sense? So that would mean for this to work, that's right. So for that to work, we have this orbital here that would have an electron, right? And so the hydrogen that would bond with it, with its s orbital, could come here, right? Cool. Just so we know that's not an orbital. That's oxygen. And then here, we would have an orbital that looks like that.
It's a dragonfly.
Here it would have its electron, right? And then the hydrogen's going to come along here, and it'll have the shared electron there, right? That makes sense? Can you picture that? For this to be true, what would the angle between these two things be? How much? 90 degrees. So this works perfectly if we can look at an oxygen atom under X-ray crystallography, which is the technique they use to figure out the angles between bonds in atoms. And if we see that water makes a 90-degree angle from hydrogen to oxygen to hydrogen, then this is good. This works. Have you ever seen a teacher say, okay, let's draw water, and it looks like this? 90 degrees? If you have, you shouldn't, because it doesn't. It does not make a 90-degree bond angle. In fact, it makes a bond angle of 109.5 degrees. Actually, sorry, that's not quite true. Actually, it makes a bond angle of about 108 degrees. I was thinking of methane. Because I lie a lot. So this doesn't work. Even though we have two bonds here, remember we said single bonds always have to be made in what kind of orbital? Hybrid orbitals. Any sigma bond must be in a hybrid orbital. Are these electrons in a hybrid orbital? Now here's the problem. If I'm going to get them into a hybrid orbital, I have to hybridize them with the s. But the s is already full, which means even though we have these lone pairs, again, this whole thing is going to be hybridized. And so since we know that, who can tell me what my next configuration is? Obviously, the 1s orbital is still unaffected because we only changed the valence. We only changed the outer shell. So we're going to end up with a 2 because we're in the second shell. We're taking the s orbital, and we're taking p orbitals. How many of them? All 3 of them. So we're making an sp3 hybrid orbital. Now, we used an s, and we used 3 p's. How many orbitals am I going to end up with? 4. Good. I find, as stupid as this sounds, I find it helpful to hold it up on my fingers. S, 3 p's, boom. That's 4 orbitals. Okay. 1, 2, 3, 4. Now, all together, how many electrons are going to fit in there? 6. And we follow whose rule? We follow Hund's rule. So 1, 2, 3, 4, 5, 6. These are lone pairs. And these will make what? These will make sigma bonds. And specifically in water, they will make sigma bonds with what? With hydrogen. Yep.
Does it matter where the down arrow is in the p row? What if you have like one at the front of
By rule of thumb, we start at the left and move up.
Could it be wrong?
I'd have to look that up. I don't know if there's an energy difference between like ML-1, ML0, and ML1. My instinct is that it shouldn't be energetically different. That's just an arbitrary rule we do for neatness sake, but I don't know that. I will look it up and get back to you. Again, I'm not a quantum physicist, not by a long stretch, but I will look it up and see if I can find a good answer to your question. Oh, I was going to draw this down here. So like, hey, there it is. Whoops. Okay. Now, this leads to our second rule, rule 2. Lone pairs always go in hybrid orbitals. So when we're talking about the valence, sigma bonds need hybrid orbitals, and lone pairs go in hybrid orbitals. Now you might be saying, Mr. Orlando, does that mean that everything goes in hybrid orbitals and we're always going to make sp3 hybrid orbitals for everything? Because we've talked about bonds and about lone pairs, and that's everything. So everything goes in hybrid orbitals? But What about the other kind of bond? We've talked about sigma bonds, which are the first bonds that get made. But the second kind of bond that we can make is called a pi bond. And pi bonds behave a little differently. Pi bonds are weaker than sigma bonds. They're not as strong. So a sigma bond, in terms of covalent, is the strongest covalent bond possible. And then when you add additional pi bonds, they do make it a stronger bond, but not to the same extent as a sigma bond. They're weaker. They also have some other properties that we'll talk about. Let's look at the nitrite ion. And of course, we already have it up there, but this is good practice. So let's draw it out. What's the first thing we do when we go to make a Lewis structure? Count them. So you count them. I'm going to do my own here, but don't trust me. You do yours. 2, 3, 4, 5. I've been coughing since November. It makes me very sad. That's okay. I'm tough. Oh, whoa! I should just like throw my computer after it and get them both together. I will get it after. Thank you very much. No, I'm taking it. Listen, I'm not above floor food. You can be proud if you want. Okay, how am I going to draw this? What goes in the middle? And nitrogen's going to go in the middle.
Wait, why not nitrogen?
So the truth is that we would think that oxygen should go in the middle. Because there's 2 of them and 1 nitrogen, you just got to trust me.
There's 2 oxygen.
Can I tell you why? It's because oxygen is normally more electronegative, but in this case, it has a -1 charge. And what ends up with the extra electron is an oxygen. And once oxygen has an electron extra, it's less electron hungry. And now because of that, nitrogen is actually more electronegative by virtue of the fact that that extra electron, probabilistically speaking, spends 50% of its time with one of each of the oxygens. Do you actually care? When there's a charge involved, things get a little wonky. Is that a fair answer? In the meantime, we have 2 oxygens, 1 nitrogen. The nitrogen ends up in the middle.
In other words, the 2 oxygens put nitrogen in the middle because it's basically
Sure. Yes. Yeah, that works. Yeah, no, like that's as good an explanation as mine was. Mine sounded more fake BS-y, but you know. Okay, so I draw bonds between them. What do I do next? Before we count, but first we've been dealing with hydrogen, so we've skipped this step a bunch of times. But now we're not dealing with hydrogen, so fill the octets. So I'm going to fill nitrogen's octet like that. No, what octets do I fill? I fill the surrounding octets. Good. So like that and like that. And Jade Barlow, what do I do now? Now we count. 2, 4, 6, 8, 10, 12, 14, 16. Almost. What do I need? I will need another bond, but before that, do I have enough electrons? So where am I going to put more electrons? So far I've got 16 electrons. I need 2 more. Where do they go? Very good. We're going to put them on the nitrogen. And now what do we have to do again?
Don't you have to do them separately?
No, we always put them in pairs. That's a good question, by the way. When we add the lone pairs, add them as a pair. By the way, you will, like if you go to Khan Academy and stuff, there's people who teach different methods. But at least how I teach it, just always add them as pairs. Your life will be easier. And now we count again. We say oxygen has a full octet. Well, we knew that. We gave it a full octet. Oxygen has a full octet. Again, we knew that. We gave it a full octet. But we were only able to add 2 electrons to nitrogen. Is that enough to give it a full octet? No. It needs how many more? 1 more bond, right? 2 more electrons, 1 more bond. And it's going to take them from one of these 2 oxygens. For the purpose of right now, until we talk about resonance structures, pick one. And I'm going to say, okay, these ones get shared. And so we make a double bond there. By the way, what charge does this whole thing have? -1. Good. Now let's talk about each of these things in turn. We have an oxygen, we have a nitrogen, and we have an oxygen. First, the oxygen. How many sigma bonds? Good. Oh, you got it. Just, shut up and you're perfect. Yeah, you're right. 1 sigma bond. What else does it have? Very good. 1 pi bond and?
Well, one has 2.
Yeah, we're talking about the first one. This one right here.
Yes.
2 what? Very good. That's perfect. All right. 2, let's talk about nitrogen. What's he have?
I thought the ones with the double bonds also have a sigma bond, so maybe 2 sigma bonds.
This oxygen is making 1 sigma bond, 1 pi bond, and 2 lone pairs. You're totally right, which is why Alondra talked to me about nitrogen. What is it making?
2 sigma bonds.
Very good. And what?
1 pi bond.
Great. Is that all?
One.
Very good. All right. And who wants to tell me about the final oxygen? Yep. Yep. I'm not going to write it, but you're right. 0. Very good. And I get lazy, so I often will just put LP for lone pairs. No, I'm not talking about long playing records. I'm about lone pairs of electrons. Does anyone know what an LP is anymore? You do. An LP is like a 33 1/3 rotation per minute record of the type you're usually, if you picture like an old vinyl record, so maybe this would say like AC, DC, and then there'd be like that little lightning bolt between them. And then like, if you look, there's like 2 sides to it, and half the songs are on the first side and half the songs on the other. They used to call that a long playing record. And so that's LP, and it rotates at 33 1/3 rotations per minute. Yep. And then the other is these things here that are much smaller, and we call these 45s. You'll sometimes hear the term EP for extended play. And a 45 rotates at, anyone? Anyone? 45 rotations per minute. Very good. Very good. And then, yeah, I have a whole bunch of old acetate 78s, and they rotate at 78 rotations per minute. As technology improved, they were able to get the rotation slower because they were able to get the resolution inside the groove itself finer and finer. And one day, if you're super curious, ask me how they got a stereo audio signal into something that's just a needle sticking in a groove, because it's pretty crazy. But we don't have time to talk about that right now.
I think you have to come me and my siblings on the little
So,
record.
all right. So, I want to talk about nitrogen here. We could draw an electron configuration for all 3 of these, but I'm not gonna. I'm gonna talk about nitrogen. Okay, so let's talk about nitrogen's ground state first. What is nitrogen like normally? What would its electron configuration be? Anyone?
What if you do 1,
And how many go in there? Yep. What do I have next?
and then 1,
Good. And then?
you leave, but you
Great. Just 1 electron? For nitrogen, how many? The 1, 2, 3, 4 electrons so far total.
Oh, so then we
Perfect. So they would go like this. I am wrong. They would go like this. Okay, cool. Now again, obviously this can't be right. because this would say we have one lone pair and 3 single bonds. And of course, we've already talked about how the orientations aren't right. We said that sigma bonds always need to be made in hybrid orbitals. We said lone pairs always need to be in hybrid orbitals. Good. So these are going to be in hybrids. Had I been clever, I'd have written them next to each other, but I'm not. These will be in hybrid orbitals. But pi bonds are always made in p orbitals. Pi bonds are made in p orbitals, which means when I go to hybridize this, I need to save one of the p orbitals. And so what happens is these will hybridize, right? And this doesn't. When we talk about the shape of bonds, we'll talk about why this is. Right now, I want you to just take it from me on faith that p orbitals are the only orbitals that can make pi bonds. Now, with that in mind, what's the new configuration? Well, we still have 1s, right? How many electrons does it have? 2. But now, let's see if anyone's super clever. Think for a minute, don't blurt it out. Let's see if we can be super clever and guess what the name of our hybrid orbitals will be. Think for a minute. What do we think? Very good. And how many little lines am I going to draw? How many orbitals is that actually? 3, because we used, and again, pathetic as it is, I always say it out loud, sp2, s, 2 p's, I get 3. Good. And then what did we leave alone? We left that 2p alone. And because we left it alone, it still has its electron in it. Does that make sense? They didn't touch it. It's still there. It's still got its electron. It's just waiting to form a pi bond. In the meantime, how many electrons did we hybridize? 1, 2, 3, 4. How will I put them in here? Very good. 1 on each, and then another in the first. And so if you look, now what do we have? Well, this is going to make a pi bond. Actually, I've been using the pi symbol, so I should be consistent. That's going to make a pi bond. These will form sigma bonds, right? And of course, the other thing left behind is just a lone pair. And you should always be able to look back at the Lewis structure, and it should match what you're left with. So my Lewis structure should say that nitrogen has a lone pair, 2 sigma bonds, and 1 pi bond. And we go and look, and sure enough, nitrogen has a lone pair, 2 sigma bonds, and a pi bond. It's not so bad, is it? Yeah.
Are you able to tell how many pi bonds or how many sigma bonds are going to be without making the diagram?
Excellent question. You must make the Lewis structure first, because nitrogen will not always have this hybridization. Nitrogen doesn't always make a pi bond. There are many, many, many cases where nitrogen only makes sigma bonds, in which case its hybridization would be sp3. In this case, it's sp2 because it's got to make 1 pi bond. So let's make a Lewis structure for carbon dioxide. So a Lewis structure for carbon dioxide. Yeah, carbon dioxide doesn't have a charge. it would have to have like it would be like an 8 ion if it, like the carbonate or the carbonite ion is CO2 with a -2 charge, but this is just carbon dioxide. What?
Did you kill my cat?
I erased your cat. I like to think he's not dead, that we just moved him to a farm upstate. Now draw a Lewis structure for carbon dioxide, please. And then, just like goldfish, you can draw a cat that kind of looks vaguely like it and just convince yourself he's still okay. Did you just replace your cat with a cat that looked kind of the same? Yeah, that's what we did when I was a kid, too. You just kept buying kind of the same basic cat shape. And then you just convince yourself that your cat's really old. Like, I can't believe she's lived to 26. That's astonishing. Oh, I like kittens.
Is anybody planning on fostering the kittens that were found from the bowling alley?
What's this?
Oh my god, the cat lady? The cat.
Okay. Oh, whoa, whoa, whoa. Okay. Okay. I got 16 electrons. Do we all say the same? Okay. 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 Come on. Come on. This is true. So are we done? Are we done? Okay, well, how many electrons do we have? Okay, good. What do we do next? Not yet. I don't think so. Not yet. You're right. Do we need that any more electrons? No. We have 16. But is oxygen happy? Why? Yeah, we made it happy. Is oxygen happy? Yeah, we made it happy. But is carbon happy? No, make carbon happy. Like, listen, carbon, we're friends. Right?
I know. Yeah.
I know you do. I have faith in you.
I just didn't know carbon needed to be happy.
Yeah, everyone needs to be.
Why does carbon?
Oh, carbon's not a person?
No.
I mean, strictly speaking, no.
That's technically carbon.
Aren't we all carbon?
Yeah.
Well, that's it. You're made mostly of carbon. So what? You want to be made of mostly unhappy things? That's your solution?
Yeah.
I feel like that most days, but maybe that's the problem. Maybe my carbon just isn't taking up those pairs of electrons. All right. So what do I need to do here?
I took you off and then made it.
Beautiful. Very good. Okay. And later on, we'll learn why this is the structure and like this isn't.
Wait, what? There you go. It looks easier for each one.
Yeah, that's exactly right. We'll talk about why. We're going to learn the rules that dictate that it's something called formal charge. Now, we're going to talk about, we could talk about oxygen, but for expediency's sake, because we got 10 minutes left, I just want to talk about carbon. What is its situation here? What does it have?
A wife, 2 kids.
It can dream one day, hopefully. In the meantime, it's got two sigma bonds and 2 pi bonds. Does it have any lone pairs?
No.
All right, let's get doing on the electron configuration. And I will give you the ground state, and I want you to hybridize this one yourself based on the rules you know. And you're even going to have to name something like an orbital you've never seen before, and I have faith in you. So in carbon's ground state, it has got a full 1s, a full 2s, and then it's got this 2p thing going on, right? Do I have that right?
Yes.
So I want you to figure out what it must look like, how it's going to hybridize, and what's going to be left with. Yeah. Yes, you can pick whichever one you want. No, just you can take for granted. The question was, when I'm hybridizing, can I kind of pick which ones I use to make the hybridization? Yes, you can. And no, you don't have to tell me that you've done that.
When you started that sentence, I thought you were hybridizing, and I was confused.
That I was
like you yourself.
That I personally was going to form a hybrid with a different orbital.
Like, that's
No. I've been fully human so far in my life, and it's working well. Though I could see advantages to being some sort of jellyfishy and hybrid. Maybe like an electric eel.
I'm thinking
I'd like to be able to electrocute people. Imagine, like, is actually your homework done? No. Oh. Like
sorry.
Cool, right? Whoops.
But
So that just keeps happening.
But with the human in the involved, you get electrocuted every time you do that.
No.
No, like
This is like a secret.
Were you watching the Spider-Man stuff? Yeah.
Oh, that is. Come on.
Okay.
What do you got?
I got it.
Done. I realized.
Love it. Love it. Wonderful.
Thank you.
Very, very good. No shocks for you. Very good.
Is that anything right?
Yeah, the only thing I'd say is you don't need that number there. Yeah, that's perfect. Well done.
See, I'm thinking both of them, and then like leaving this last guy out. I don't know.
Well, how many pi bonds do we have to make? So how many p orbitals do we need to keep? 2. Hey, do we have a couple p orbitals that are ready and waiting for an electron?
Yeah.
So let's keep those.
Okay.
But we have a 3rd p orbital. What are we going to do with that? Well, you can't get rid of an orbital, but the ones that we don't keep, we're going to hybridize, right?
Okay.
So we're going to use the S.
So would I use the S in this last one, and
That's right.
these make a bond with each other, or are they on their
They're just
own?
waiting to make pi bonds, rather. You've got it. You're there. Let's draw this one out together, and then the homework you're gonna get lots of practice doing your own. Okay, so guys, let's do this one together. So obviously we're only talking about the valence, so 1s remains unchanged. Now when we get to the valence, how many pi bonds is this going to make? 2. And this is how other teachers teach it differently. This is how I think. I have 2 pi bonds. So keep 2 p orbitals. To me, the easiest thing to do is just to count the pi bonds, and that tells you how many p orbitals we need to keep. And I'm going to highlight the p orbitals I'm going to keep. So I'm going to pick the ones that already have electrons in them. Does that make sense? And then everything else, I'm going to hybridize. And what's left to hybridize? Well, the S, and there we go. So what are we going to call the hybrid orbital? 2sp. Sometimes people write like sp1. It's not wrong, but it's not like we write s1p3, right? So the accepted nomenclature is just sp. Now, we've taken an s, we've taken a p. When we put them together, we will get how many orbitals? 2. Hey, how many electrons did we have between those 2 orbitals? 2. But now we're following Hund's rule, so we're going to put them in how? Very good. And then what did we not hybridize? That's right. We have 2 of the 2p orbitals left, and they still have 1 electron in each.
We got left.
And now these are ready to make what? Very good. That's exactly right. And these are ready to make what? Very good. It's a little brain bendy. You guys did really well. You followed along very well. Proud of that. It's not too bad, is it? For homework, I'm giving you the same Lewis structures I gave you last time. So if you did your homework the other day, you've already got the Lewis structures you need. Okay? What I want you to do now is write the hybrid state of everything that isn't hydrogen. All right? So write an electron configuration. And I'm going to say hybrid configurations. For everything. So when you do a Lewis structure here, you've got P and Br and Br and Br. I want you to draw what will be true for the P and what will be true for the Br. Now in this case, all three Brs are identical, so you just have to write one of them. Does that make sense? But if you get to something like NO2, are those oxygens the same? No. So you're going to have to write an electron configuration for the first oxygen, and you're going to have to write an electron configuration for the second oxygen. All right?
What if the third word? Oh,
yeah. And you can skip hydrogen. All right? If you're really keen to do hydrogen, it always looks like this. Hey, done. All right? So if you want to do hydrogen, there's your cheat sheet. Every time. She might want to come for some one-on-one help. Yeah, she might want to come for some one-on-one help. Yeah, no problem. Well, I'm